So this is the last section in the chapter 1, and this one is not covered in our textbook, but the symbols, introduction of the symbols could be useful for your future learning. This one is to show you the conventions, how to symbolize the components of the stress. And again, we have calculations already. We know that in magnitude, the stress equal to the force divided by area. And this one we've been calculated, been exercised is we always exercise in two-dimensional scenarios. But actually, in general, the stress, these concepts can be applied to three-dimensional, and that is the purpose of this section. So here, we start with, here we define our coordinate systems, x, y, z, like this. And here I show you, this is, let me call this is a plane. So you can see here is the plane. This plane has the normal vectors. This plane is normal to, has a normal which pointing to the z direction. So here for this one, I call this called the z plane. Okay, and for this one, this plane has a normal pointing to x direction. So let me call this is called the x plane. And in the similar, this plane is called the y plane. And why we want to identify the x, y, or z plane? Because in each plane, that has a corresponding cross-sectional area. So we need to identify which orientations of the cross-sectional area we're talking about. Okay, so let's start with the x-plane. For x-plane, you can see this is the component, and this force component is normal to the x-plane. So the normal stress will be induced by this force. And on the other side, we have two components of the force. This is pointing to z direction. This is a force in y direction. So here, this is, let me call this is a force Fx, and Fy, and Fz. And that the three force components are so unique, and they're basically independent from one from another. And this will induce normal stress. The two will induce the strain stress. This force is parallel in the cross-section pointing upward. So this will have the strain stress, and in the plane pointing upward, this will have the strain stress in this plane pointing in the z direction. So here I come to the point we can use symbol to define the stress component. So this one will have induced the normal stress. So in general, we use the tau, and this one, again, this tau is not to indicate the strain stress anymore, but with the two subscripts, we're going to have more generic definition. So this one basically saying is this. The first component is saying is the which plane is lies on. So right now we talk about is x plane. And the second component is to indicate which direction is pointing to. So in this similar way, we can label this one. The corresponding, the induced, the stress components by this force, you can see the first symbol is which plane is lies on. For this one is x plane. Direction is pointing to y direction. For this one, the induced the stress is, okay, this one still, this one in the x plane, and pointing to which direction, z direction. So therefore, in the x plane, we have three different, in general, we have three different stress components. Normal stress component, two strain stress components. And we can exercise on this one. So now, again, this one, this is the normal stress and induced by this normal force. And in which plane?
Y.
Y plane, and pointing to which direction?
Y direction.
Y direction. Good. So this one is in y plane in
X
direction. This one, y plane in
Z direction.
So the same thing here. So this one is in z plane, pointing to z direction. So So this one is in Z plane and
X
direction, and in Z plane, Y direction. So in total, we have 9 stress components. Non-stress component, basically here, if you could imagine, so say if this is certain material, I try to draw in 3D, and then this one is under any kind of the loadings, and then, for example, if we're interested at this point, and then we can pick up, around that point, we can pick up a small cube to describe the distribution of the stress. And this small cube, basically in concept, just like we did here. Okay, so in total, nothing more, nothing less, we use non-stress components to describe the status of the stress in general 3D case. And non-stress component here, basically here is tau xx, tau xy, tau xz. We can write into the matrix form. The first row is xx, xy, xz, is this one. And the second row is yx, yy, yz, is this one. The third row is zx, zy, and zz. So the third row is about the z-plane things. So again, in mathematical expressions, we can use 3x3 matrix and to contain the non-stress components. Okay, and so that is for the definition of the stress components here. And if we look at the stress element in one way, so for example, we look at from the z directions. This is kind of the complicated drawing, but don't be scared of by those symbols. Basically, this indicate is, you can see right now this is a z plane, so this is the plane has normal to x direction, so this is x plane.
Oh, yeah.
Right now,
Okay.
if you look at the cube basically growing up in this way. So this is a plane.
Mm-hmm.
The plane has the normal direction to x direction, so this is the x plane, and this is a y plane. In this x plane, we have the normal stress tau xx, and in our textbook, simply using sigma x, but that's okay. And in the x plane, this again, this is x plane. This is the components in the x plane pointing to which direction?
Y direction.
Y direction, so that's tau x1.
Okay.
Okay. Again, this is a y plane. Again, this is the cube going in this way. On the top, the plane is normal to y direction. We call the y plane. Okay, so that stress component is in y plane, pointing to x direction. Tau xy, tau yx, and that are they are different stress components. And in a similar way, here this is x plane, so x plane pointing to y direction, tau xy. In the same way, this is a y plane pointing to direction yx. And in this page, and again here, this is a one stress component, another stress component. Okay, they are different. And again, in stress component here, we're showing is here tau xx, tau xy, tau xz. Let me rewrite. And for this one, tau xy, in terms of our expressions, that locates here. And for this tau y, tau yx, that location is, in our expressions, is here. So basically, I want to show you they are different components. In mathematics, they indicate is the different attribute. And one is, this component is the distribution of the stress in this plane. And the other one is on the other plane. So basically, they are different entities.
Okay.
And however, I can show you in magnitude, although they are the different entities, but in magnitude, they are equal. Okay, and they are equal is we can, in our textbook, simply we take the equilibrium, the moment about the z direction, because the whole element must be stationary, shouldn't be rotating. Otherwise, we won't study statics. The mechanics of material we're going to study is vibrations.
Right.
Okay, so here we have to make sure everything is in static. So keep everything static in equilibrium in magnitude. This and this must be the same in magnitude. Okay, so here again they are different entities, but in magnitude they must be equal to maintain the static equilibrium. So that the same thing here, this magnitude this entity in magnitude must be equal to this one, and the same thing, this magnitude should be equal to this one. So basically, if we do everything right, if we put it into the matrix representations, that should be 3 by 3 and symmetric matrix. Okay, symmetric matrix. And these properties, sorry, here should be tau. And this property is going to be used later on in a few incidents. And then to that moment, I will point out one more time.
All right.
Okay, so just keep in mind. And for example, here, so say if we have a stress element like this, x, y. So this is an x plane, this is a y plane. For example, if say you will be able to calculate the string stress at this plane is say equal to 5 MPa, then for the remaining work you don't have to repeat your work. Right away you can just write it out. This is the 5 MPa. And this one must be converged in direction to the point here. And this tail is away from, so on this side it is tail away from the corner, the same magnitude, 5 MPa. The same thing here, 5 MPa. So if you know one thing, you can right away to write up the other 3 components, and that is the application of this